Harald's or Chris's talk. And yes, so this is basically an offer how to have an easier way to understand quantum social science, application of quantum theory in social sciences. Our plan for today is to delve into quantum tic-tac-toe, which is actually a game devised by a physicist, Alan Goff, to introduce, basically for teaching purposes, to introduce quantum theory to students. And it's very nice, at least from my point of view, it's very nice introduction to quantum theory. So our idea was to introduce the game, then to let everyone to play it, to have some experience with quantum principles, and then, yeah, crucially, to draw some insights of what we can learn from this game with respect to quantum theory. So if you do not object to this plan of today's session, we will go directly into quantum tic-tac-toe. You probably know what tic-tac-toe is, but quantum tic-tac-toe is basically quantum analogy to a classical tic-tac-toe, which is there to illustrate some key concepts of quantum theory. And especially it allows us to get some experience with key concepts like superposition or entanglement without actually engaging with the math of quantum theory. As I said, the author and one of the leading sources that you may use to better understand quantum tic-tac-toe is Alan Goff's article published in American Journal of Physics. But yeah, I will try to make the introduction myself so we can engage in the game without reading the paper. First of all, I need to start with the classical variants because tic-tac-toe, I believe, is known around the world. But for example, in Czech Republic, you will play it differently than what is the US version of it. So I will introduce this US version, which quantum tic-tac-toe is the analogy to. So you may be familiar with that, but still, so we are on board, and also that we start to develop the language that we will further use to understand quantum variant of the game. First of all, there is the 3x3 grid on which the game is played. We have two players playing either crosses or circles. They alternate to mark empty squares with either cross or circle their mark. And one move in the classical variant of the game means that one square is filled, completely filled with the mark. And you probably know the way how to win the game. So the first player who gets 3 marks in the row, either horizontally, vertically, or diagonally, as you see on the picture, wins the game, which means that if you play the tournament, you will get 1 point, and the other one will get 0 for losing the game. When all 9 squares are filled with the marks, the game is over. And if there is no winner, it's possible that no one has this row of 3 marks, horizontally, vertically, and diagonally is a draw. And usually in tournaments, you have 0 points for having a draw. So only when a winner gets points from finishing the game. Now, that's simple, but let's look how it looks like in the quantum variant. In the quantum variant, we will need somehow bigger grid to play on, but it's still only nine squares. But in each of them, there are more like smaller scales to place your mark on, and it is because one of crucial rules in the quantum variant of the game, which says that you can place 2 marks on separated squares, and it is called spooky mark. So, for example, I learned from last year, so I will try to draw an example so we can better understand the game. So, for example, sorry, it doesn't work. I will try to do. So, for example, if I'm an X player or a cross player, I will, in the first move, I will actually make 2 marks on 2 separated squares. They are called spooky marks. I used subscript 1 to clarify that this is my first move, and we are actually creating some kind of entanglement between those 2 marks. So my 2 marks, that means squares 4 and 5 are now somehow entangled in the game because I mark them with my spooky marks. Then if I go to the second rule, so if there is another player, I will use another color for him or her. New marks can be placed on square occupied by other spooky marks. So the fact that we have a spooky mark here in square 4 doesn't mean that I cannot play there, but that means that the other moves becomes entangled with the previous ones. So if I, for example, place the circle here in the second move, and for example here, we create two spooky marks which are somehow connected, and because O2 and X1 shared the 4th square in the game, we actually have 3 squares that start to be entangled. Yes, Michael?
You should maybe say that these little squares have no real function. They just serve to, maybe explain.
Okay, thank you very much. I forget about that. So these green numbers, I add them only because we will use them to specify what squares we talk about. Yeah, so they are just like numbers of the squares, and they are in this zigzag way from 1 to 9. So for example, spooky mark X1 is the superposition of the marks on square 4 and square 5. So that's only for us to better communicate what we are doing in the game. So we said that every move in the game means placing 2 spooky marks. Then new marks can be placed on the same square as the previous marks. Then the third rule, which will introduce the concept of cyclic entanglement. So for example, if I place the third move or the second move by the X player, but third move in total in the game here, that means that those two are once again connected. And that means that overall in our game, we close the circle of the entanglement, which means that the game will collapse. And the way the game collapses is that if I, as the X player, creates this cycle, the other player, that means circle player, will select how the game will actually collapse. And in the collapse, only one of those spooky marks will become realized in every circle. Yes, Michael?
And maybe it's good to add that what closes a circle, it's not important that X closed it with an X, so it could also be O with an X. I mean, so whatever way the circle is closed.
I have some examples in the next slides as well. But whenever basically you can create circle with 2 pairs of spooky marks, is the smallest one, and with 3, then with 4, and it goes bigger and bigger. But whenever you close it, that means that it becomes the full circle. The game will collapse, and there are always 2 ways how it may collapse. So for example, here in this example, we will have, I will start with square number 4. We either have cross here from the first move, or a circle here from the second move of the player. So one of the players, the player which will not create the circle, will decide. So for example, let's say that O player will decide that O2 will occupy a square. That means that X1 will not be here, but will realize in the other option, which means that X3 will not realize here, and it will realize in the last option. And O2 is already placed here, so it's no problem that you will animate this as well. So if there is ever a circle of the entanglement, that means that the game collapses to classical marks. So we will have bigger marks that will occupy the whole square. And when we have a classical mark there, we cannot place another quantum spooky mark to this same square. I will give you more examples of these circles because they are the key in the game. And the last one, how do you count the points in the game? So the goal is once again the same. You will win the game if you achieve 3 classical marks in a row, either horizontally, vertically, or diagonally. But because of this entanglement, it may happen that actually 2 or more rows are created in the same moves, in which case the player who needed more moves to achieve the row gets only half point. So if, for example, we create a circle, we create 2 rows of the same marks, but my moves were later on in the game, so I will get only half of the point. I will give you, because this circle of entanglement is somehow difficult to grasp, so I will give you the example. So here I have some variants of the game. You don't see the numbers of the squares here, but I will use the numbers as well. So here we have a move of the first player, which is the circle player, and he or she placed her spooky marks in the first and the fourth square. And those 2 are connected. They are in superposition. Then X player can play, for example, this move, placing the spooky mark in square 4 and in square 7. Then let's say that the player with squares continue creating the circle but not closing, with the spooky marks placed in square 5 and square 7. And now imagine that I'm the player with the crosses, and I thinking about creating the circle. I actually have 3 options how to create the circle. You probably see it. So one of the options is that I will place the other spooky mark in the square number 1, and I will create the circle created by 4 squares. Or I can place it here, where I will create the circle created only by 3 squares. And that's weird to say that you create a circle by 3 squares, but okay. And the smallest one is if I only connect back to the same cell which has been created there. It has the consequences, because if I, for example, select this one, then there is actually one spooky mark which is outside of partially part of the circle, but also outside of it, which means that it will necessarily collapse to the other option, because otherwise, if it collapses this here, it will not be allowed in the game. I can show you how it propagates, but so it's not out in the circle, so it will collapse in O1 in the first square. That means this option is no longer here. And now, as I was the cross player, the circle player is about to play, and he or she will decide how to collapse it. So Michael, how would you collapse the game to be it in your favor for crosses? You are muted.
How should I collapse it? I am O, right?
No, I am. No, so you are O, yes.
Yeah. So I will collapse it on the middle, on the 5th.
Yeah. So as I close the circle, the other player here, Michael, picks O3 to be in the center of the game. That means that X4 will not realize there, which means that X4 has to realize here, which prevents X2 from realizing here, and X2 will realize here. And O3 is already placed here, so it's not a problem. So many times it is possible to collapse the game. Always there are 2 options, and if there is some spooky mark which goes out of the circle, it always has the value of the mark there. Yeah, so I just wanted to clarify that if I, for example, am in this position, I can collapse the game with 3 different cycles, these 3, or I can continue expanding the game and not collapsing it in the classical moves. in the game, in the spooky marks like this. Yeah. So this I wanted to clarify, and now our idea was that we, with Michael, will show you 1 or 2 mock-up games. So we will show you how it works out, and then everyone, then we will create breakout rooms, and everyone will have option to play the game. So we are 6 here, so we will create 3 pairs, and we can play the game. Is it okay for everyone, or is something unclear so far?
I think it will become clearer when everyone plays. It's
okay. So I will give you. This is the software which you can use to play the game. It's the same visual as we used in the slides. You can decide whether circles or crosses started as in the classical game. And so I will leave it to Michael to start.
okay. So I can go first. So X goes first, I think, right?
Sorry?
X goes first, okay.
Yeah. Mm-hmm.
So I will entangle 4 and 5.
Okay, perfect. If you play the spooky marks, you have to click pass, and then you will pass it to the other player. Yeah. So in the second round, it's me, and I like to occupy the center. So I will try to place my spooky mark there, and I will continue expanding, exploring the space with spooky mark here.
Okay. Okay, well then I can close the circle so that we see how it works. So I will place 1 here, yes, and and 1 in number 4.
Okay, you see that everything is gray because you cannot place another spooky mark. You have only 2 options. And if I click pass, then there is a circle. It's not visualized there, but you should be able to see it with the help of my visualization. And it's up to me, as Michael created the circle, to measure it. So as I said, I like to occupy the center. So I will select O2 and will measure it, which means that O2 will collapse into the center, and the other 2 will be occupied by Michael now, because O2 is in the center, it cannot be here. So the 2 remainings will be Michael's. But yeah, I could choose another option, but I like the center. Okay, so it turns to classical marks. That means they occupy all the space. And now I continue with spooky marks, but I cannot place them here. I can choose only from the 6 remaining squares. So I will try to play here, and here trying to get one of the diagonals.
Okay. Then I will place it at your last one. And maybe at the very first.
Okay, good. Okay, so no circle created. Sorry, you have to pass it. I will go to the square number 1 and to the square number 9.
So now I can close it maybe. So I will put it in the 3rd.
Here?
Yeah.
Okay.
And then the one like in this number 7, it should be. So this should close it.
Yeah, so there will be this triangle or circle. What happened now? I clicked measure, and there was this triangle, and this one was out of the triangle, so it collapsed to my marks. And I'm not so sure why X5 collapsed here, but there was, I believe, only one option there as well. And now I can decide whether O4 or X7 will be placed here, and the other option will realize here. The problem for me is that no matter what I will select, Michael will win the game. So I will click measure here, but Michael had the other one. So The result of this game is actually Michael gets 1 point for realizing 1 row in classical marks, and I have 0 because I did not achieve the same in the same round of the game. Yeah, would you like the rematch?
Yes, yeah. I mean, up to you.
Okay. Okay, so let's try another one, a more complicated game. So I will go first, and I will start with the one of the
Okay, so I do in the middle and in the right next to it. Yeah.
Here.
Mm-hmm.
Okay. Now closing the circle was not a good idea, so I will expand. So I will continue here and here. So I have more chances to get the central square here.
Okay, so I will close a triangle.
Mm-hmm.
I think so. Yeah, here number 2. Yeah, yeah,
Mm-hmm.
and then the next row, the first, like number 4. So this should close this triangle.
Mm-hmm. Okay.
Mm-hmm.
So I will just try to visualize it. So there is this connection, and this connection, which means that these 3 are creates a circle, and this one stands out of the circle. So if you pass it, then this should collapse to the classical mark, because it's out of the center, and it eliminated the mark that was here, and now I can measure it, and yeah, I will definitely have the center now. So I will keep it with the first move, and will collapse I will have this one as well, and Michael goes up with the measurement. Okay. Now I have to pass it. No. Yeah, sorry. I started. So I continue the game with trying to get the bottom row.
Mm-hmm. Okay, I put in the very last one too.
This one?
Yeah, and number 3.
Okay. Okay, so I will create a circle or triangle here. So I will connect these. These are connected and these are connected. And it's up to Michael to decide.
Which one so I can measure. Yeah, so I can measure either the number 9 or the number 3, right?
You can measure whatever. Yeah, but usually you start with your own marks where you want your.
I can also measure yours.
Yeah, you can mine, but it's only 2 options. So no matter which one you choose,
Right,
you will
right.
collapse
Okay.
it somehow.
That's right. So I measure my upper one.
Okay. So we want this. Okay.
Okay, measure.
Yeah. So you have, and I have the 2 remainings, and I do not have much option for the next move. So let's place the marks. Michael.
So
you do not have much option either.
So wait, like okay, then I can 1 and 8. Yeah, I can do the same.
Okay. That's the only option that is remaining.
Right.
But yes, and
well, then we have to measure, no?
yeah, and now we are measuring.
Yeah.
I think we changed the moves now,
yes,
but we play the same, so
it's fine.
No difference.
Let's measure.
Which one?
Oh, the first one.
Okay.
Yeah.
So Michael is creating a row of his marks with this classical move. And okay, so the game collapsed. we filled in all the marks, classical marks. The game is over. Michael is once again the winner because he has the row of crosses, but there is another row of circles at the bottom. So in this case, the last rule I had on the slides apply, which says that who achieved the row later or latest will get only half of the points. So here my row of circles was created in the move number 5, number 7, and number 9. So the latest one is 9, and Michael is only 8. So even though Michael started the game as the second, he achieved to get the row of marks sooner. So it would be 1 point for crosses and half a point for circles here. Yeah. So we hope it clarified the game. I will go back to the slides. And so what is the idea now? The idea is that we will create the breakout rooms. Please go to the breakout rooms you are assigned to, and you will meet another person there randomly. The way how you play it, the game, you open the link. I will provide it in the chat, so you can open it in your browser. But then please share the screen. Sorry, I sent it only to Michael. It's wrong. Then please share. Sorry?
Can everyone share their screen then? Like only one person would have to share the screen, right?
One person will open it and share the screen, and the two will play it.
And can everyone share the screen? Do they all have the rights?
I hope so. This is what we asked Kelly for.
Okay.
But in the breakout rooms, like always, one person should be able to share the screen in the 3 breakout rooms. So please to open it, try to play it. If you have any doubts what happens in the game, try to talk about it, try to clarify what is happening there. The game is not intuitive, but you hopefully will get some intuition out of it once you have some experience with it. If you have some questions or doubts, please keep some log. You can print screen or just recall what happened, and we can discuss it once you return to the main room. And the idea is that we will allocate about, yeah, it's 15 minutes, but since we are only 3 groups, I will limit it to 10 minutes, and then we will discuss it. Yeah. Okay, so any questions? If not, I will create the breakout rooms. And Michael, please join breakout room as well. What is it?
I can see it, the window is create.
Okay, so you can create it now.
It popped up. So 3 breakout rooms, right?
4 now.
Oh, okay, good. Okay, then I click on create. Looks good. Well, there's one room with only 1 player. Doesn't make sense, right? I can join this room, number 4.
Yeah.
Hello. So let's move Christine to our room. Okay. Hello, everyone. I'm Christine, and wait. Hey, Azad, can you hear me? Hello, is there anybody in there, out there? Hello, is anybody in this room and can reply? Okay.
Eva and Martin, where are you from?
Oh, so as you probably know, I'm from Poland, so I'm actually staying in Warsaw.
Okay. Yeah, I could guess from the name.
Yeah. But I know Charles University very well, so maybe you know Injich Krejci?
Sorry?
Injich Krejci, so maybe you know Injich Krejci. So there is at the Charles University and the Czech Academy of Sciences, there's a data archive.
Yeah.
And the head of this data archive is my friend from 20 years or something. Yeah.
Okay, great.
So I've got a lot of relations to Czech Republic but also Slovaks through the fact that I'm the head of the Polish Social Data Archive. So we meet each other, you know, a couple of times a year. So, but I'm a sociologist, so. Interested in physics from many years, and so I'm very happy that I found this bootcamp because I was doing it by myself, so I was learning by myself. But it's something different to hear people who are involved in this much more at the much higher level than me. So it's really appreciated. So it's very interesting.
Okay, great. Yeah. Great. I've closed the room, so we will have 3 angry participants here in few seconds. I'm sorry, I must have closed your breakout room, but if you want to finish the game, you can do so now. You are muted, Michael.
Yeah, we just finished. It was perfect timing, actually. Yeah. So
okay, perfect.
We just lost 2 people, I think.
Okay.
But okay.
That happens all the time if you try to make Zoom calls interactive somehow.
Yeah, people are
okay, guys. So I hope you had some experience with the quantum world now. Was someone able to get some winner point in the game or more? What was the score in your group, Michael?
Yeah, we just could play 1 game. I mean, it was a very intricate game, and or did we play 2? I don't know, but yeah, one of us won, and it was we actually had 2 rows, you know, at a perpendicular, but
okay.
by the same person. So
that's great. That's great. Okay, so it was just a quick introduction because we are almost out of time. I will just try to make some metaphors of it, but I really encourage you to play more with this game, to play it with friends. And also at the end of the session, I will give you the link to other quantum games. There is, for example, quantum chess, which I really like. So I will give you some ideas around this, but I would like to talk for, let's say, we started like 10 minutes after 8, so I will try to, in 10 minutes, to go through the metaphors that we can learn from this game. There is, if you see the Goff's article, you will see that there is actually a number of metaphors that he talks about. But I would like to talk about 4 most, I would say, prominent, which is the idea of quantum state, idea of superposition, idea of entanglement, and then the collapse, which is the transition between quantum state to classical state. Just to stress here, as we have a lecture on cubism, that we will build on mainly Copenhagen interpretation of quantum theory, which is the standard interpretation of the theory. So we will not go into like novel understandings of quantum theory, but we will try to match the game to the I would say, the most prominent interpretation that exists among the physicists in the physical science. So let's talk about these four metaphors. First of them is quantum state. I'll just minimize you to see the slides. Or what we can, it's actually why is it all on the slide? Okay. What we can see in the game is that it's actually something what gave a quantum theory its name, is the fact that many observables, physical properties that you can somehow measure, are not continuous but quantized. So for example, if you've had energy of the atom, it comes in quanta of energy, so it has certain levels. And according to Goffman article, here in this game, it's similar, because you have actually something what's called quantum state, which is represented as the vector, as we will learn later on in this tutorial. And this vector would be specified by your action of marking the square n in move I, and it would be denoted with this letter psi and this weird ket notation by Dirac. But it's only some notation that we will highly used in this tutorial and in quantum theory. But basically, the point is that, so if you have for these numbers for individual squares, individual cubes in the tic-tac-toe, then you will, for example, for the mark in square n and move 1, you will play so if I place x1 to the first square, I can write down the quantum state of the game as psi equal to this 4 in quad notation subscript to xy. I can then expand if I continue with the game. That means that I create other aspects of the game. I add other components of it. I can write the state of the game as the product of these two, and later on of these three works. Sorry, I've prepared the game that it should like write the explanations down, but it seems that everyone is on the slide, which is kind of confusing for me now, but please bear with me. That you can see all slides now. Oh, so the idea is that we will describe
I think Jakub is frozen. Or is it my internet?
No. So it's Jakub's.
Okay, we will write in a...
So it works by me. So
Okay. I just wrote him a message. So I mean, unfortunately, I don't have the slides. Otherwise, I could continue. But I mean, the notation is pretty clear, pretty straightforward. It's just how to write down, like in chess, when you write down the moves. Okay, I think he's joining again. Oops. Okay, so he probably logged out and he will log in again. Otherwise, any questions I can address in the meantime?
it's clear.
Okay.
As for me, so.
Okay, I have a quick question because I was looking at something else. So the classical notations of vectors were the first one was 4 greater than x1, and the second one was there was a 4 and a 5. Were those the positions on the board?
Yes, this was the positions, and this greater than, this is just has nothing to do with greater. It's just a weird or strange notation which is used everywhere, so we use it too.
What is it called?
It's called the cat, like a cat. It's a word. So it's very loud here. So it's just a word play. which a physicist Dirac introduced, and he made a word play between bra and cat, and because there's a way to sandwich quantum states and to get out a number. So as quantum state, in the way one usually writes it, is in the cat form, I think, and this is what this larger than signs mean. So it has nothing to do with larger.
I didn't think it did, but I just didn't know how else to state what it was.
I will talk about this in the next part if you still intend to join. But otherwise, now Jakub is online again, so you can also ask him once he has a slide up. Okay, welcome back, Jakub.
Yeah, I'm really sorry. My internet just went off. I don't know.
I will switch you to co-host again. Make co-host. It's fine. Happened to me last year too.
I'm really sorry.
No problem.
I don't know.
So there was a question.
Okay.
About your notation.
Okay. So what's the? So you addressed the question, or?
I think. Okay, we have to ask. Was it Eva? Did you ask a question?
It was me. So I was just wondering on the notations, the 4, 5, 6, 2. They're showing yes, that is actually correspond to the board number, and that's all I was trying to determine.
And I'm sorry, and what's the question, or?
On the classic tic-tac-toe,
Mm-hmm.
the vector equations, I was just trying to determine what the numbers 4, 5, and 2 that were in there, the large numbers. I just was trying to make sure that they corresponded with the space on the board. And
So now we are describing the classical game. So for the x1 mark, we have this vector which specified x1 mark was placed in square number 4. And so far we have no spooky actions, no quantum moves there in the game, only classical one. And yeah, we can like develop the notation of the describing the game in this notation, using this direct notation as adding other moves in the game to the quantum state describing game. But I will just show you on the next slide how it will change for the quantum game. So the idea with the quantum world, that instead of one classical mark in one of those cubes, you allow for the superposition. That means linear combination of 2 of these classical marks. So with spooky marks, I can create, for example, this CXY, which is some linear combination of x1 being in the square number 4 or x1 being in the square number 5. This is just some normalization factor, which I choose to normalize it to the probability of 1 across both the options. But in quantum theory, you would have to compute in the game. It has different meaning, which I will hopefully get to if we get there. So I can just expand the notation that I can create this quantum state of superposition. That means linear combination of 2 quantum moves, and can both code them into the quantum state. When I add another one, and these 2 are not entangled, and I will get to entanglement in a minute. So I have superposition for O2 marks. So it's either or not either, but both in the place in the square 3 and square 6. And so there's the probability that either of them will realize as the classical mark. And if they are not entangled, we can write them as as a product term, which means as the multiplication of the 2. Which brings me to the third point, which starts to be really interesting with respect to this quantum game, which is the idea of entanglement. So if we follow this logic, so let's not focus on the text, but on the picture. So we can create one spooky action two spooky marks on squares 4 and 5, which are specified here. And with the second move, all player can place the second mark, but now in cubes 2 and 5. And as I said, if those two are ended up in the same square, these moves actually become to be entangled. And I will try to give you some intuition. What does it mean? So I said that we can write the overall state of the game as the product of the two moves that happen in the game, but it's not possible if they are entangled. And I will show you why. So if I write the product state of these two, I will end up multiplying the first term, which specified that x1 will be either in the square 4 or 5. And the second one, we specified that the moves will be on the other, either in the squares 2 and 5. If I multiply it, which I can, you know it from the basic algebra, you will get these 4 terms, which combines the terms from both brackets. But actually the last one of them is the move which is not allowed in the game. So the last combination would means that the square 5 will be occupied by both x1 and o2, meaning in classical marks, which is not possible. There is only one classical mark in each square. That means that I have to eliminate this part from my state, and the overall state or overall quantum state of the game can be described like this. So we have the first 3 terms from the explanation above, but we do not have the last one, which means that we cannot write the overall psi of the game as the product of the two, because and this is one aspect how you recognize entangled state in algebra, that it does not allow you to factorize 2 parts. So it does not allow you to factorize it into 2 parts. I'm not sure whether I make sense now, but hopefully we will clarify it later on in the tutorial. And the last aspect, last metaphor I wanted to specify. So if we have this entanglement, so we can create the circle. So now we do not have only squares 4 and 5 entangled, but also 4 and 5 and 5 and 2, which means that also 2 and 5 are entangled because they are all connected with these pairs of spooky marks. And it means that we can, if we want to expand this, there will be lots of terms if we multiply them, but actually many of them are not allowed in the game, and there are only 2 options that are allowed in the game, which is how the end will collapse. So I will show in the slides if it's possible. This is what I tried to show you at the beginning. So this circle, it will be player O, which will collapse the game, and the O will decide that O2 will be either in the center or in the top, and the rest will collapse based on this choice. So what I wanted to clarify here is that there is a really nice metaphor or connection between the quantum word and the quantum tic-tac-toe, because it's allow you to develop a notation of the quantum states. It introduced the concept of superposition, because those two spooky marks are in the superposition to each other, or they are in superposition, so in linear combination. We can create entanglements. So if the two marks are placed in the same square, that means that the other marks are entangled as men, that they are no longer independent on each other, because they will collapse. The way how one collapse will influence the way how the other collapse. And the last one is this transition between quantum and classical world, which says that if you have this quantum word and you observe it, it can no longer exist in superposition of the observables, but only one of the observable will realize. And this is what happened in the game. The metaphor is not perfect, mainly because I will just say two things why it's not perfect. One of these is that ideally the game would correspond to the classical game in all instances, which is not possible in the game. So for example, according to the rules of the game, it's not possible to place both spooky marks in one square, which would be the classical move. Yeah, so I would create a circle with myself and will let it collapse. So it would allow me to play the game classically if I want to. But in theory, there is a limit how to get from the quantum to classical version of the game. So the more often there are measurements, the more the closer the game is to the classical one. So in theory, when in every move you measure it, it will turn out to be the classical game. So there is this correspondence which would work well, but it's unfortunately missing in the game. Yes, Marcin?
Yes, okay. So I've got a question which probably comes from the fact that I'm not a physicist. I'm not physicist, so, but but it does not matter. So regardless the rules of this game, I mean this let's say two-dimensional game, because it's a kind of I perceive it as a kind of a two-dimensional game. So you said about the spooky marks and that they can be in superposition, but the question is, if it is theoretically possible that three spooky marks stay in superposition, which could be expanded, I think this game could be expanded into a three-dimensional game, and in this case, it would be possible to have three of them. But is it theoretically possible, or for some reason not?
Yeah. You have a really good point. Yeah, that's another way. So the number of elements in the superposition are limited to 2, but in quantum systems it can go to whatever number or even infinite, or even continuous variables for observables like position or momentum.
Even continue. Okay.
Yeah. So that's the structure of quantum formalism is not limited to 2 dimensions. This game is. Yeah, that's
okay. Okay. So thank you.
You have a really good point with respect to this.
Yes, thank you.
And since we are out of time, I will just give you that's what I said basically. I just wanted to give you references to the other games that you can quantize. There is we played this. This quantum tic-tac-toe. The other one does not seem to really work, but it allows you in theory to play it online with your colleagues. But if you are interested, there is also quantum chess application. The first 2 are paid, but the last one is online. And what is funny about this game, if you know chess, you may be interested in trying to play this, because it means that your figure has 2 identities. So you will play with king or with not king, it's not a good example, but for example, a horse or castle. And only by clicking on your figure, you will realize which one it is. So it creates lots of uncertainty in playing the game. And only the king is the figure that has a certain identity. It's a king in all aspects of the game, but then all your figures change the identities all the time, and it's very difficult to keep track on what's going on the chessboard. So if you know chess, then you try to go somehow into the world of quantum uncertainty, then you are welcome to try this. Okay, sorry for the I will leave it here, so we will have some break before the second part of the tutorial. Sorry for the technical troubles. I did not expect they will happen, but after 3 years of COVID and everything, it seems that these continue to hunt our work.
Okay, thanks a lot, Jakub. Yeah, no problem at all. Thanks for everyone for staying. So we will have a 10 minutes break or 9 minutes and resume at half. Yeah, so Jakub, if you would like to leave, it's fine. I mean, I will just talk about what I presented last year, and it will be very basic, like vectors, complex numbers, and at the end a little bit of visualization, what a quantum measurement is. So everyone is welcome to join, of course.
Mhm.
So let's see who will be back in 8 minutes. See you.
Thank you. See you.
Thank you. See you.
Guys, I might have to leave in a little, like 30 minutes, just to let you know, but thank you.
Okay.
Thank you.
Mm. Okay. Can everyone see my slide? Yeah.
Yes, it works well.
Okay,
Yes.
good. Yeah.
Yes.
Alrighty. So let's start. Okay. So as I said, this is are we recording? Actually, recordings should still work, right?
Yeah, it's still recording.
Okay, good. Because somehow I'm in full screen PDF mode, so I don't see much. But I think I see if you raise your hand. So so this talk has 4 parts. First, I will talk about the vectors, vector spaces. Then part number two is complex numbers. Then about quantum states, how they are defined, this strange bracket notation. And in the last part, I will give a first idea how to think about classical versus quantum sets, and tomorrow there will be a continuation talking about classical versus quantum probability. Okay, what is a vector? This is a vector, we call it V. So in a nutshell, it's an object which has a certain length and it has a direction. And it resides within what we call a vector space. So it's not just in the nothingness, but it resides in a container. So vector space it's called. And this container can have a certain dimensionality, which is often called D. And in quantum mechanics, this dimensionality, so it can be 1-dimensional, 2-dimensional, like here on the plane, 3-dimensional, and in quantum mechanics, it's often infinite dimensional. But in quantum cognition and quantum game theory, it's typically low dimensional, like 2-dimensional or 3-dimensional, something like this. When we talk about directed objects, what one can look at is the opposite direction. So this would be called the inverse vector. It's inverse because if you add these two, they give 0, which can be represented just as a point, as 0 length, 0 direction, or undefined direction. And then with a vector, you cannot just add them and subtract them, and we will talk about this later, but you can also stretch them. So you can multiply them by a number, in this case, a real number, like 2 or 3 or 4, and or minus numbers too. And later on, when we have introduced complex numbers, then vectors can also be, in principle, multiplied by complex numbers, but one thing at a time. So in here, it switches the direction because it has been multiplied by a negative number. So if you multiply the vector by 2, it doubles its length. And if you multiply it by minus number, it just flips its direction. Please, if there's anything which is unclear, just raise your hands and interrupt me. So examples where vectors appear in everyday world and are useful and intuitively make sense is like forces. For example, when you build a bridge or so, you need to balance all these force vectors. Again, they have a certain strength in a certain direction. Electrical fields, of course, velocities. When we drive our car, velocity has a strength and a direction. Acceleration too. For example, here, this boat crosses the river, so there's a certain velocity generated by the for the person inside of the boat, and then there's superposed another velocity from the stream, and these two add up to a resulting velocity. And so the question still is, why should this be useful in social science? And of course, we know that somehow it has something to do with the way we think about quantum mechanics. And when we do look into quantum social science, well, then it will be necessary. But there's also application without all this quantum thing. And this is when it, when it comes to thinking about representations of categories. So since vectors can be distinguished by their direction, well, you can use them to characterize or to distinguish categories. And the cool thing is, when you use vectors to distinguish categories, you can also do all the other stuff which you can do with vectors, namely combine them, add them, stretch them, and so on. And this seems a bit abstract, but okay. So first we will talk about how to combine them, add, like here, addition and subtraction. So I cannot hide video panel. Oh no. Right, show me. Right. Okay, so here is about adding. So the way to add them is to just write these vectors in a sequence, and and then just concatenate the tip with the bottom of the next, and then you get a resultant vector, which is just the added object. The same with subtraction. You start U, add the B, and then to subtract the W, just add the inverted W. So this would be the inverted W, you just add it. And this would be your resultant. And where this makes sense, for example, and we will have a talk about this on Thursday, is in natural language processing. So, for example, I will explain a bit later, we will have now for each of these concepts a vector. And then once we have this, we can do things like subtract concepts, like king minus man plus women equals what? Do you have a question? Do you have an idea what this could be?
A queen.
A queen, very good. Good. Some, like last year when I asked this, somebody that wrote in the chat, it will result in peace. I found it funny. So, and this is based on, so people have done this in recent years. This is called vector representation of meaning and of semantic. And as I said, maybe we will have a talk about this on Thursday. Dominic Widows will talk about natural language processing. So if there's a way to when you have a large database, this is what this author did, to find which words semantically are close to each other, and once you have a sense for the neighborhood and for the distance, then you can start to position them in a low-dimensional space. So here it's 3-dimensional, could be 2-dimensional, 4-dimensional, and then you can just do, because then these concepts are points in a high-dimensional or low-dimensional space, and you can just add them and subtract them, just as we did. And then indeed, you can do like exactly what is written here. You can subtract, like king minus man would be this green vector, then plus the women would bring you here, and then you would get this yellow vector. This would be the left side here. And then you see that in this database, at least, okay, it's not exactly pointing in the same direction, but it's almost there. I mean, so it kind of captures a structure. I mean, when we do this, when cognitively it makes sense, but it's interesting to see that also the data would support this, even if it not perfectly. So now with Paris minus France plus Poland, you can do the same. Marcin, I should ask you.
Yeah, Napoleon, I think, but
What is it?
Napoleon.
Napoleon. Yeah. Okay, now we're getting second order. Okay, Warsaw should be the answer, and cars minus car plus apples, apples, right? So each time it filters out a different structure. Yeah? So it's interesting. So these type of abstract operations on applied to concepts somehow make sense. And this is also why they are useful in social science, even beyond a quantum framework. Now, another vector space is real numbers, like number in general, like real numbers here, and then complex numbers. Because take any number like A and B, you can do the same what I just described with the vectors. You can add them, subtract them, and multiply them by another number, stretch them. So this is how it works. You add them, subtract them, multiply them. And then so far, these vectors, they lived in this vector space, but so far we haven't introduced more structure. So, but if you introduce a so-called reference frame, then you can also represent these vectors by means of their coordinates. So, but in order to talk about coordinates, you need to specify a coordinate frame. And this coordinate frame is never unique. So you can choose one, but then if you rotate it, then it's a valid other coordinate frame. So, but your coordinates will change. So your coordinates are always defined with respect to some given coordinate system. And this is how it works. So we have a two-dimensional vector here, and it has two components, Vx, Vy. And this also works in 3D and in ND. If there's any question, please interrupt me. I mean, this is very basic, but for somebody who has never seen this, it's not basic. So it's fine to ask questions. Once we have a notion about the coordinates, there's a nice way to calculate the length of each vector. Namely, this goes like this. We can just apply, first the length is always a number which is larger or equal than 0. And if given a vector with a given certain length, if we multiply it by another number, lambda, then also its length will be multiplied. So this is in a sense the requirement for a valid length measure. And I have to say that there are various possible definitions for length. So there's not a canonical, I mean, there is one standard, which when you know Pythagoras theorem, this is what you would first apply, but there are also other ways to define a length. And we will talk about this in the next slide. And the interesting thing also is when you have two vectors, and you can also ask how are they oriented to relative to each other? For example, are they parallel? Are they orthogonal? This is an important question. So we would need a way to specify angles between vectors. So in the following slide, I will explain how this is done. First, let's look into the length. So Okay, we have this vector. How can we define a length? Well, Pythagoras' theorem says you just so to define the length of this vector, which would be represented by this edge C, you just add its x coordinate squared plus its y coordinate squared, and then you calculate the square root. Okay, as I said, this is just one way. This would be the Euclidean norm. There are other norms which we won't talk about it here. In 3D it works the same, and in ND the same. And this is also the norm which is used in quantum mechanics. So now if we have the coordinate representation of two vectors, we can look at calculate the inner product. This is defined like this. Don't be scared about this way of writing it. It's the so-called bracket notation. I will talk about it later too, but you just multiply each coordinate and sum them up. This gives you a number, a real number. So it can be negative, can be positive. And you can show, I cannot explain it here, but it's not difficult to see, that this number, whatever it is the length of the first vector times the length of the second vector times the cosine of alpha. So this applies for real vector spaces. For complex spaces, it's a bit different. So we know that, for example, if they are perpendicular, then the cosine of alpha is 0. Then this number here should be 0. We will also talk about this on another slide. Just wanted to mention it here. So cosine and sine, in case high school math is a long time ago. So just it's a representation of the what happens to the x and y coordinate when you imagine a unit circle in a two-dimensional plane, and you just take this point and rotate it around. So it's x-axis, which is described by the cosine of theta, here marked in yellow. So it starts out at 1, in blue, sorry, it starts out at 1, then it decreases at 90 degrees, it's 0, then it goes negative, and so, and the y coordinate does the same with a phase shift. This would be the sinus. As I mentioned, orthogonality. If the angle is perpendicular, the cosine vanishes, and therefore also this inner product vanishes. And this is important in quantum mechanics because whenever we have to make a projection, the way projections are done is a perpendicular projection, and which involves this inner product. We will also see it a bit later. Then a certain class of vectors are unit vectors. They have length 1, and they will become important because quantum states also have length 1. In 2D, this means these points are arranged on the unit circle. Yeah, so these are all different unit vectors, all having length 1. And then, as I mentioned, whenever we want to talk about coordinates, we need a coordinate system. And so a coordinate system of choice would be in a d-dimensional space, like 2-dimensional here, given by a set of d vectors, in this case 2 vectors, which are orthogonal to each other. And by combining, adding and subtracting and stretching these basis vectors, you can in principle reach any point of the here 2-dimensional space. The basis vectors don't have to be orthogonal, but it's much easier when they are. So this would be a canonical orthonormal basis. For example, 1, 0 would be this, and 0, 1 would be this vector. So these have the property that their scalar product is 0, so they are orthogonal. And when you calculate the inner product of a vector with itself, what results is the length squared. So since here it's unit vectors, the length squared is always 1. And then the cool thing is, if you have a vector, any vector, you can decompose it according to these bases. And how this is done? Well, you project it. And how do you project it? You calculate the inner product. This will be explained here. So in order, assume you don't know its coordinates yet. So just imagine this Vx and Vy is not there. So we want to calculate it. And all we have is the vector V and we have the basis. Okay. Well, in order to calculate the x coordinate, you calculate the inner product of V with this vector, Ex, and you get a number. And this is your coordinate. I mean, it looks almost trivial, but conceptually, there's an extra step here. And the same with the y coordinate. So, I think I think this is just what I explained on the previous slide. So the cool thing is, if you don't know for the coordinates yet, and you want to calculate them with respect to a given frame of reference, that's what you do. You calculate the inner product. So, okay, we don't need to go. This is basically what I just explained on the previous slide. And in 3D, again, you can generalize this concept of unit vectors. So instead of tracing a sphere, no, a circle, they will trace out the points on the sphere. So again, different examples of unit vectors. Again, we have a canonical basis. This time it's 3 vectors. Again, so 2 different basis vectors will be orthogonal, and their length is 1. And again, any 3-dimensional vector can be decomposed in terms of this basis. Yeah. So this would be the first part of the talk. Now I would come to speak about complex numbers. So if there's any question to the first part, please let me know. No question? Okay, Marcin.
Yes, so can we think about these vectors like about some kind of correlates of some phenomena?
Some kind of what?
Some kind of correlates of phenomena.
Yeah, so phenomena is fine. Yes, whenever you can quantify it, then because at the end, a vector itself can stand for a phenomenon, but what makes a vector useful is when also in this phenomenon like space in which you describe the phenomena, you can also have a sense for a basis, like which by combining this basis you can reach this phenomenon. So and then so
maybe I will help you referring to the direct well-known analysis which is performed on the ground of social sciences, like factor analysis. So
okay.
factor analysis. So factors are let's say kind of correlates. Yes. So it also it of course depends. Yeah. So it's not so easy, but in general sense there are some kind of correlates of some social phenomena. Phenomena, and by analyzing data in this way, you get from your data set different factors, which I always imagine that they are some kind of vectors, because they can be correlated, they cannot be correlated. It depends, yes, but there is some kind of relation between them. And this relation comes from the simple fact that the source of them is in the same data. Yeah. Yeah. Okay.
Yeah, it seems to fit. So of course, when like there's like a projection going on. I think when you look into, I'm not exactly sure what you like. It would be helpful to have an example, but if you look at factors, it seems as if you have something high dimensional and already you project it down so that you can understand what is going on, what type of, and then two different phenomena would land in a different space, but they would already land in a quantifiable space. And then you would be dealing with vectors because you have projected it down into a vector space.
Yeah. Okay. So this clarifies me. Yeah. So that's, so I would say, so transferring this to my knowledge about data analysis in social sciences, it would be a kind of a combination of factor analysis with a regression analysis, because regression analysis contains this element of prediction. Yeah. So it's not just a pure cross product of the data. So it's something more.
Yeah.
Yeah. Okay. So, but yeah. So thank you.
Yep. You're welcome. And any other question? Okay. So now come the complex numbers. So we have seen in the first talk that with the real numbers, we can do two things. We can combine them, add them, and we can multiply them. And now, but the real numbers are, we can think of them as one-dimensional objects. Like they are, when we think of numbers, we have something in mind, like a line, which stretches from -infinity to 0 and then to +infinity. So now the question is, can we do the same with a plane? So, and the answer is yes, and you can do even more. So, but let's see how this works. So a complex number has a real part and an imaginary part. So here, this would be a complex number. 3 would be its real part, and 2 would be its imaginary part. So you can think of them as a point in a two-dimensional space. And then it's multiplied, the imaginary part is multiplied by I. And I is called the imaginary unit, and it has one feature, that I times I equals -1. So you see, when you take the product of this imaginary unit with itself, it gives you something which lives in the real part, like in the real number. So this may, if you see it for the first time, may be a bit strange, but in a sense, That's all you need to understand complex numbers. Because you can take two of these numbers, whatever it is, it can be, here it's 3 and 2, it could be 8 and 9 and so on, and then you can just multiply them as you would. And whenever in your multiplication you have I square, you replace it by -1. And then you know how to multiply these strange complex numbers. And now there are two ways of representing them. One is as points in the plane, as I mentioned, and then there's another one. So it's, yeah, the other one would be a polar representation. We will talk about this later. So first, let's take this point, 3 plus 2 times I. So this is the imaginary axis. So the I, you can look at it as a vector pointing in this direction. And here the 3 is actually a 3 times 1, and the 1 is just a vector pointing in this direction. So this is where how you make the relation to vector spaces. If you take another number here with a negative real part, you can do the same. 2 minus I, well, has real part 2 and minus 1 in the imaginary axis. And so you get the idea. And then the real numbers, of course, they are part of these complex numbers because they have imaginary part 0, right? So they are embedded. So the complex numbers, therefore, are a generalization of the real numbers. Then, as I mentioned, there's a basis. So we can look at this number system of complex numbers again as a vector space, and then we can give a basis. So the 1 and I would be the basis vectors. And now how to calculate them with them? You can add them just as you would add the vectors. And for the multiplication, it's not clear because what I presented in the first part only talked about how can you take two vectors and add and subtract them or multiply them by a real number. Now here we want to multiply two complex numbers. So we still have to explain more structure. So the adding is very simple, just as you would add the vectors, nothing new. And the multiplication, now it's interesting. And I just gave you the recipe how to do it, but this is the easy way. One can also, the hard way would be to think of how would one be able to multiply points in the 2D space. And then there are several ways to do it. And one solution would be this one. But this would take a bit of time to demonstrate it. So if you take the recipe, you will know how to multiply them, but you will still not understand exactly what is happening. So let's build an intuition for this. Let's first just blindly apply the rule. So let's have a complex number u here and v. So now let's multiply them. U times v, okay, you know. This is 1 times I, gives I, plus 2 times I times I. It's like 2 times I square. We know this is -1, so gives -2 plus I. And this is our result, okay? So if we visualize this, we have U and V, and this would be the W. So there, does anybody who has not seen complex numbers yet have an idea how to understand what is happening here? How you can graphically see that multiplication of this vector and this vector gives this vector? Any idea? Once you know it, once you have seen it, it's easy. But when you see it for the first time, it's a kind of aha moment. So the way to to geometrically understand what is happening when you multiply two complex numbers is that their lengths multiplies and that their angle adds. So we will have still to define what angle are we talking about. So, and this is where the polar representation of complex numbers comes in handy. So instead of decomposing a complex number into its x and y coordinate, we now decompose it into its length and its the angle it forms with the x-axis, which we call alpha, and the length we call, it's just the norm. You can call it magnitude or modulus or norm. And this angle is also sometimes called the phase in complex mathematics, or the argument. Okay, so we had this vector u, or this complex numbers u, and now we multiply it with v. Again, this has, here it has 90 degrees, and it has length 1, because it's just a very simple example. And now, I just told earlier that the resulting vector has a length which is the length of both multiplied. Well, this has length 1, so basically it will have the same length as the vector u, which is the case. And then the angles add. So we know that the vector v had 90 degrees. So if we add 90 degrees to this angle, to this vector, well, you see, you just get the w. So it seems to apply. But yeah, and I just answered what this question. So of course, at this stage, you have to believe me, because otherwise it would take too much time. But I think building an intuition for this is easy enough. And if you need the details, you can just look up on Wikipedia. Lengths are multiplied, phases are added. That's all you need to remember. And for more general complex numbers, you can just do the math, plug in the numbers, calculate it blindly. Whenever I square appears, you replace it by -1, and then you will get this rule that yeah, for these two numbers with real part A and imaginary part B and real part C and imaginary part D, well, when we multiply them, this will be the new real part of the resultant complex numbers and the imaginary part. So this is a rule how complex numbers are multiplied in order to yield consistent multiplication, consistent division, and also assure the embedding of the real numbers together with all the operations which are possible in this complex number systems. Then complex numbers have one operation which doesn't exist in the real number system. Because in the real number system, we are just, it's a one-dimensional object. So in complex numbers, since they live in 2 dimensions, they allow another operation, which is obtained by the mirror reflection at here the x-axis. It could also be the y-axis, but it's defined like this. If you take this vector and you just invert it at the x-axis, then you get the complex conjugate. And this is also important because now if you multiply these two, you get always a vector which is real. So, and this will be important whenever we calculate probabilities. And it's not just real, it's real and positive. That's important. So, and in quantum mechanics, this is interesting. Whenever you, at the end of a calculation, you want to come up with probabilities, often what you will see, you multiply a complex amplitude with its complex conjugate, and then you will get a probability, which is always larger than 0 and smaller than 1. So I wanted to mention this. Then another thing I would like to mention is Euler's formula, just because it's so aesthetic and important too. If you have never seen it, it's worth to look it up again in an analysis textbook or Wikipedia. It is a way to represent complex numbers with length 1. So they live on this unit circle, and their real part is given by the cosine of alpha and the imaginary part by the sinus of alpha. And it can be shown that they can also be written in this exponential form, where instead of having a real number in the exponent, like e to 2 or 5 or so, you have a complex number. Of course, when you see this for the first time, you don't know how would you work with this, but there's a way to show that this object here is identical with this complex number. It's far from obvious, but it's not hard to show. It would go too far here. So the way to show it involves you have to look up the Taylor expansion, and then you can prove that this identity. And it's a very nice identity because it means every complex number with length 1 can be written in this very compact form, which is called complex phase. And these complex phases, you will see them everywhere in quantum mechanics. And also for the special choice of alpha equals pi, 180 degrees, then you can show that e to the I pi, which is just -1 plus 1 equals 0. So this, or it's equivalent to say that e to the I pi is -1. So it relates two transcendental numbers, the Euler constant pi and this imaginary unit with a real number. So it's, some call it the most beautiful formula. Okay, so this would be the end of my second part. And now I would talk about quantum state. Are there any questions about complex numbers? Marcin?
Not
You're my default. Okay. Have you seen complex numbers before?
So I heard about it and even read about it.
Okay.
But that's it.
So I hope this helped a little bit.
Yeah.
It takes a little bit of familiarization, but they are really not nothing dangerous or nothing to be afraid of. So, like in reading through the Wikipedia page, you after half an hour you will get a good feel. Okay, a quantum state is a vector with length 1, and the thing is that now here, instead of just multiplying the vectors by real numbers, stretching them by a certain factor, we can also multiply it by complex numbers. That's the type of vector space we are interested in quantum mechanics. But it doesn't change much. And to be fancy, from now on we will write these vectors in this Dirac notation. So it's just another fancy way of writing a vector. So I bring it up here just to get used to it. So psi and minus psi which before were inverse to each other, here, when it comes to quantum mechanics, I mean, they're still inverse to each other, but they refer to the same state. So in quantum mechanics, it doesn't matter to the category of a quantum state remains the same if you invert it. And even more, if you multiply it by I or minus I, so and by any complex phase, it still refers to the same quantum category, to the same quantum state. So and you can only multiply it by complex numbers which have whose length is 1. So that's the only restriction. Why is this the case? Because in quantum mechanics, in quantum physics, you cannot measure the phase here. You cannot tell, is it pointing in this direction or in this direction? So because the probabilities at the end all boils down to probabilities, they will involve a squaring operation, which will remove all information about the phases. We say that the complex phase of a quantum state is not observable. So therefore, this equivalence class, how it's called in mathematics, refers to the same quantum state. Just mentioning it in case it comes up in a textbook or so on quantum mechanics. Then the corresponding vector space now is called the Hilbert space. And what is a Hilbert space? It's just okay, just a second. It's just a vector space with inner product. Machine.
Yes. So I've got a question. I've got a question concerning the previous slide. If you
Okay.
could. So does it mean that the complex phase of a quantum state is unobservable? Does it mean that if it is observable, then the observation leads to the collapse of the wave function? No, it's something.
No, it doesn't mean so. And no, there's no observable. Like there's no which you could come up with, which would tell you. Which would take a quantum state and tell you this is its phase. It's not possible. Because at the end, yeah, it's, so it has nothing to do with the collapse.
Oh, okay. Yeah.
So the Hilbert space, also nothing scary. It's just a vector space which has an inner product, like a scalar product, defined. That's it. Vector space. So the inner product is an extra structure imposed on the vector space. The vector space without inner product defined is not yet a Hilbert space. Okay, so what is this all good for? This brings me to the, I think, the last part of my talk. So now from now on, it gets a bit more easier. So from now on, no math anymore, almost. So when we think of categorization, we typically have instances like data points or whatever, and they are distributed somewhere, and we want to order them, to group them. For example, we can look at these cities somewhere in America, and when we look at them, well, we will see that actually they reside in different states, located in different states. Indiana, Kentucky, and Ohio. So, and this stands for any type of classification problem, I guess. Here, this would represent a classical representation, or think of classical physics. So here you have like particles, and they have attributes attached to them, like labels. This particle is of this type, or here this city is belongs to this state and not to the other. This is a represent like a instance of the classical way of thinking. Elements have attributes, and they are either they fall into this class or not. So there's a certain type of Boolean logic which applies to these sets and subsets. However, in a quantum world, it's a bit different because there, whenever you ask element what category it falls into, for some elements, each time you ask, you may get a different answer. For other elements, it may be pretty constant. So there's like a certain fuzziness. And the question is now how to learn how to think about this. Where does this fuzziness comes from? Because it's not a not knowing. It's not like a noise. It's like something more, like a bit deeper. So let's build an intuition for what would a quantum city mean. So these dotted circles now represent these quantum analogon of classical cities. Okay, so before we ask a city, we apply the state measurement operator. Each city's state is ambiguous. Now we ask, for example, this one city here, Indianapolis, what state do you belong to? Okay, it says Indiana. We ask the same for Columbus and Lexington. Okay, they belong to their states. And once we ask them, a certain fact is established as the outcome of the measurement. So this means that if you right after asking or measuring the state, here the stateness of the city, if right after establishing this measurement, you ask again, you will get the same response. So there's a certain type of consistency and of persistence here. So you establish a fact. In a sense, measurement, one can say, creates reality. This is also in line with certain interpretations of quantum mechanics. And we can repeat this for all the other cities. And for some cities which are closer to this boundary, sometimes they say they belong to this other state. Right? So, and if we would just then wait long enough so that the state is forgotten and ask again, then maybe we would get another result. It's only in the process of measuring that identity is created. It wasn't there before. This is a bit strange. Yeah, so if we wait a long time, like which is longer the decoherence length, again, and it has to do with how this quantum system evolves over time. Whatever was measured is forgotten. And again, the state would be in an ambiguous, undefined state. Of course, all of this is to be taken with a lot of grain of salt, not literally, but I just try to give a intuition for how quantum states and quantum sets differ from the classical notion of sets. So if you would measure again, we would get a different outcome. And so different realizations. And then over time, if we repeat this thousands of times, we will get a certain histogram. So for the cities here in the bulk, we would almost certain they would be in the same category, but those near the boundary would fluctuate. So how can the framework we developed before with the vectors how can it be useful to represent this? And this is how it goes. So we need two things. We need a way to represent these elements, and we represent them by vectors. So each city will be represented by a normalized vector of length 1. So here, just for demonstration, we assume a 3-dimensional space, but it could be higher dimensional. Okay, so each of these dots gets assigned a certain state, quantum state. And then we need another thing. We need also the representation of the category. Like in here, the 3 states, and they correspond here to a basis vector, which is orthogonal. Orthogonal because Ohio and Kentucky are 2 categories which are different. So in this sense, they must be orthogonal. They are mutually excluding. Ohio can never be in Kentucky, and Kentucky never in Ohio. So whenever categories are mutually exclusive, they form an orthogonal angle. So here is 3-dimensional because we have 3 states. So now we can, the nice thing is here that the categories, the way that categories are represented and the states we want to categorize are drawn in the same framework. So both the states and the categories are represented by vectors. That's a nice thing in the quantum formalism. And now we still have to come up with a probability. What happens when we measure the stateness of these points? Well, the probability are obtained by Born's rule, and there's as an outcome of projections. So, for example, Columbus, this vector Columbus here, it has a certain projection, like a relatively large projection on the Ohio axis, and also on the Indiana axis. What is hard to see here, it's assumed it has 0 projection on the Kentucky axis. So it's hard to tell from the figure. But therefore we can just look at the problem in the Indiana-Ohio plane. Here. So Columbus has a certain projection on Ohio and Indiana. And now what is the likelihood if I measure the stateness of Columbus to land in Ohio? Well, this is given by Born's rule. It's just the projection with a scalar product of this C vector, Columbus vector, onto the O state squared. And the same with Indiana. And in this case, the probabilities sum up to 1, as they should. And now the interesting thing is once, this is where the quantumness comes in. Once the state is measured, Columbus ceases to be this state here, it collapses. So it either will point, if I measure Columbus to be located in Ohio, it will then be replaced by an Ohio state, at least for some time. And if the same, if I measure Indiana. So this is called the collapse of the wave function. So before the measurement, it's in a superposition state. Then say I measure O, so it says Columbus is in Ohio. Okay, then Columbus will be in Ohio and actually will point in the Ohio direction. So there will be no uncertainty anymore. And this will apply for every other observer. So it creates a fact in this sense. Marcin, ask your question.
Yes, so I have a question because probably I don't understand correctly. So what is the basis of these projections? Because so we can think about it like, let's say, I'm sorry for that, for this comparison, but like a kind of a soap, yes, soap. So you eat something and there are some potatoes inside.
Yeah.
And but you know, so there is a probability of getting only potatoes, which depends on the, let's say, how deep you put the spoon into the soup. Yes, let's say. You know, so I don't know it. I didn't measure it, of course, but we just can imagine. And in this case, because okay, so I can understand that Columbus is but there is something which maybe not determined, because it's probably especially in the field of quantum theory, it's not the best word, so it's not deterministic, but there is something what stays, what is the basis for this projection that Columbus is qualified as belonging to Ohio, not to Indianapolis or Kentucky. And how?
Yeah, not really. I mean, Columbus is, according to this, it can belong to both. It's like it doesn't really know. It's as if it's a bit both. It's like I compare it sometimes to a child. A child has a bit. When you ask certain people, they say, "Yeah, this child looks like their father, this like their mother." So, and of course, it's neither nor. It's its own entity, and to your soup. So it would be in a superposition state. And tomorrow we will see a bit more how this works. But the analogy to your soup is like, not like you fish something out and you don't know, but even before you don't know, it is either a potato or a carrot. It's not like this. The moment you fish out, it's by the fishing out that it assumes identity. And before, it can be either potato or carrot, but in a strange other legume. It's like a kid is its own entity. It's not a mixture of father and mother. It's something on its own. So it's like I don't know, like a mixture of a genetically engineered potato carrot before you measure. But since you have never seen a potato carrot, if you look at it, it's either a potato or a carrot. A bit like this.
Okay, so this I can understand, but if I would say the state does not exist before the measurement, because this I think we can sum it up to this sentence, that it does not exist, then the belongings of particular cities should, so the cities should be randomly assigned to states, and they are not, because you showed this let's say not map but the circle, and we can differentiate it by colors, that it's not randomly, so it's
it's not random.
That the prediction is more or less good, yes?
Yeah, so it's not random. So otherwise it would be like random. So it means like there's a certain propensity, for example, for Dayton to if I measure it, most of the time it will decide it's in Ohio, and there's a certain structure there. But the quantum superposition or the quantum state is able to incorporate or to express a certain ambiguity, which is not 20% of this and 80% of this, because this would still be a mixture of two categories. This ambiguous state stands for its own. It's a legit state. It's not a mixture. So as your child is not 30%, it's hard to express, but this is why the mathematical representation of superpositions is much more better apt to describe the difference between an ambiguous state represented by a superposition and a mixture state. And typically, by using words and intuition, when we think of ambiguity, we think of classical mixture, which is not it. Yeah, and it's a very important difference in quantum physics. Yeah. I'm not sure I answered your question, but the act of observation forces it and changes its state, changes its identity. It changes. Yeah. Did you want to say something?
If I may,
It creates.
It creates. You can state it. I mean, many physicists would not go so far, but there have been physicists who have, like Wheeler says, that's what, yeah, it's a participatory universe, and by the act of the observer, by observing, participates and creates reality.
if I may add one sentence, I think the analogy to quantum tic-tac-toe is quite good here, because you know, this superposition is this spooky mark, two spooky marks there. It's limited to only two, but if we have Ohio as a superposition, sorry, Columbus as a superposition of Ohio, of being in Ohio or being in Indiana, that means that basically both of these potentialities exist in this richer quantum spooky state. But once someone decides to measure it, or once the measurement take place, one of those potentialities is realized and it becomes a true observable. But that means, yeah, I'm just saying that, you know, there is this quantum state which is richer because it has both of these potentialities, but only one of them is realized when measured. So I think the quantum tic-tac-toe really works as a nice intuition to what Michael is presenting now.
Yeah. Okay. I hope this gives a taste. I mean, it takes a while to get used to this, but after a while it becomes very natural. Okay. I think that was it basically. Also, I mean, we ran out of time. Yeah. So, and tomorrow we will continue and explore a similar thing, like the difference between classical ways of thinking about probability and quantum probability. Okay, thanks for hanging in there. Thanks for your questions. Good night, Jakub and Marcin, if you are from Poland. I don't.
Yes, thank you very much. This is extremely interesting, you know, and I really admire that you are able to answer the questions of people who are not involved, in fact, in such kind of analysis. So for me, this is not something new, because I already told it to Jakub that I'm interested in this field since many years. I even started this in my PhD, which was 10 years, more than 10 years ago. But this was I think this was the first article in Poland where the Heisenberg rule was mentioned on the ground of social sciences, because I was doing research on interviewer effect. And for explaining interviewer effect, I tried to explain that it's not a measurement error. This is a part of the measurement. This is something what is inseparable, in fact, from the let's say true value, which is, you know, nobody knows what does it mean, the true value of measurement. So and I referred at that time to Heisenberg rule, but my advisor was not very happy about that. And since that time, I was looking for more information, in fact. But this is very hard, you know. So I live in Poland. So I finished some summer school at Michigan University, but I live in Poland, and this is very hard to talk to to people who are related to physics in Poland, because they think in the old way, you know, and they don't understand these relations to social sciences, which I can understand, because also social scientists, they do not understand the relations to physics and quantum theory. You know, this is something in Poland. This is something completely new. So I'm really very happy and really very thank you that you are so patient to, you know, to answer sometimes stupid questions. But to get to know about something, there is a stage when you always ask stupid questions, and this is a very good starting point, you know, to ask stupid questions. So
there's no
thank you.
no such thing. Yeah, there's no such thing as stupid question. I mean, as I was like looking through the slide, when you hear about these things for the first time, all of what I presented today is far from trivial. Of course, for somebody who has done it for 20 years, it's
So
very, but it's not at all. And so yeah, and also what you were mentioning, it's a subtle point that there's randomness and there's randomness. There's noise, which is just randomness, and then there's like a structure of what appears to be randomness. And this structure, this type of noise, if it comes from quantum mechanics, it has a structure which you can measure. And this, I think, Jakub and will talk about it on Friday, and also who will talk about it is all the quantum cognition talks, and Joyce on Thursday. And there's, you can define what is called the QQ equality, which shows that especially in these questionnaires and polling order effects.
yeah, yes. I wrote this article about the analysis of order effect in Hilbert spaces.
Yes, and there's a very nice relationship one can predict, and one finds it in the data. And this, when I first saw this, I thought, okay, the guys with their quantum cognition are really onto something. But because it's a prediction which comes out of quantum theory, has no fitting parameter, and you see it in the data. That's kind of amazing. So this may relate to the problem you looked into in your PhD thesis.
Okay, so
okay, thanks.
I'm waiting for the next session. But I wanted also to say that I visited Mershon Center at the Ohio State University, and I had some set of lectures on data weighting as a way of correcting samples in surveys, because usually I do surveys, so this is so that's how I found, you know, this bootcamp at Merchant Center. Yeah, okay, so don't want you to spend too much time at the computer, especially that you are probably tired. So thank you very much, and see you tomorrow.
See you tomorrow, and have a good night, everyone in Europe. Thanks, Jakub, for hanging in there too.
Yeah. Michael, see you tomorrow.
See you.
Tomorrow.